Hello, future engineers, subscribers, viewers, and students. There is another video about the construction of the shear force and bending moment diagrams. This is a challenging one, and I hope that you can follow the solutions and the explanations. So you have to clearly listen to the explanations because some of the details of the solutions are removed so that you will have to listen carefully to the explanations and the solutions for you to completely understand the construction of this diagram, the construction of the shear force and bending moment diagrams. So we have a trapezoidal loading, and I will divide this trapezoidal loading into two triangles as shown. So the length is 6, therefore the centroid of this smaller triangle would be through B, 2 meters from the left, and for this bigger triangle, 2 meters from C, so 2 meters from B also. And these are the equivalent imaginary concentrated forces, but we cannot imagine or we cannot do it in the construction of shear force diagram. It should be distributed forces. So summation of moments about D equals 0, Bx is 0, so By times 7 clockwise positive plus 26 times 1 is equal to this area, 1/2 of 3 times 45. The moment arm is 2/3 of 3, 2 meters, plus 1/2, 6 times 45. This is 2 plus 3, so 5 meters moment arm, plus 1/2 of 6 times 15. The moment arm is, because it is passing through B, so that's 7. So solving for By is 157 kilonewtons, which is this shown. So summation of moments about B equals 0, counterclockwise positive this time. So it is RD times 7 equals 26 times 8 plus 1/2 of 3 times 45 times quantity 1 plus 4, so 5 plus 1/2 of 6 times 45, that is 2 meters times 2, plus 1/2 of 6 times 15, it passes through B, so 0. Solving for RD is 116.5 kilonewtons. So it is also balanced by summing up forces vertical. So next is to compute this area in the preparation of the construction of the shear force diagram. So this is WB, denoted by WB. This is the details. So we have a triangle here. This is height of this triangle is WB minus 2, WB minus 15 rather. WB minus 15 as to 2 meters equals 45 minus 15, so this is 30 as to 6. So WB is 25 kilonewtons per meter. So that's why you have 25 kilonewtons per meter there. Therefore, the area is 1/2 negative. So 1/2 of quantity 15 plus 25 times 2, so negative 40. The area of this load diagram is negative 40. For this load diagram, the area is 1/2 of quantity WB, which is negative 25 plus negative 45 times 4, so negative 140. 1/2 of 3 times 45 negative is 67.5. So those are the areas of the load diagram. So beginning with A, the tangent here is negative 15. Remember, the slope of the tangent on the shear curve corresponds to the load, intensity of the load above. So that's why you have negative 15 initial slope, not 0. Therefore, the area is negative 40. So from 0 to negative 40, we connect this curve with a second degree curve, smooth curve. So beginning with, because the intensity of the load increases negatively from negative 15 to negative 25, that means that the slope of the tangent line to the shear curve is from negative 15 to negative 25. Joining this, so this is negative 25 slope, this is negative 15. Joining them with the smooth curve, second degree curve, so that's the curve. And this is negative 40, the area. Then there is a concentrated upward force here of 157. So negative 40 plus 157 is 117. Then 117 plus negative 140 is negative 23. Then to connect these 2 points with a second degree curve, the initial tangent here is negative 25, remember WB, and the tangent here is negative 45. Much steeper but negative slope. So joining these 2 points with a curve tangent to the initial tangent and the final tangent, or you just describe that the tangent line is increasing negatively from negative 25 to negative 45. So that's the curve. And this is negative 23. Negative 23 plus negative 67.5 is negative 90.5. So joining these 2 points with a second degree curve, the initial slope is negative 45. This is this. And the slope here is 0 because the intensity is 0. So joining these 2 points with a smooth curve from negative decreasing slope. So that's negative, negative, decreasing, decreasing until the slope is 0. So negative 45 to 0, negative decreasing slope. So that's negative decreasing slope. Or you connect this point and that point. The slope here is negative 45. The slope here is 0 or horizontal. So that's why we have to make the curve tangent to the initial and the horizontal slope here. Then negative 90.5 plus 116.5 is 26. Between D and E, there's no load, so it's constant, 26, and minus 26, so that closes 0. So that's the shear force diagram. Now for the moment curve, we have area 1 here. Remember, you cannot apply directly the area of spandrel because the initial tangent here is not horizontal. So it is negative 15 to negative 25. So, however, the area is negative 40, those are negative 40 then. So let's solve for area 1 into two ways. First, by defining the shear equation in AB, and that is, so I call this W. We have similar triangles here. This is W minus 15, and as to X equals 45 minus 15 is 30 as to 6. So that's why W is equal to this. So W is 5x plus 15. 5x plus 15 for the part from here to here, 5x to 15. So when x is 0, so 5x plus 15, this is it. So when x is 0, 5 times 0 plus 15 is 15. When x is 2, 5x, 5 times 2 plus 15, so that's why you have 25. So applicable only for this part. So the shear equation, therefore, is the area of this trapezoid, negative 1/2 of x times quantity 15 plus w, which is 5x plus 15, as from this equation here. So it is negative 15x minus 2.5x squared. Since the area of the under the shear curve is area of the load diagram, so it is integral of the shear equation here, shear AB, which is this negative 15x minus 2.5 x squared. So the area height of strip is equal to this thickness of strip dx from 0 to 2. So the area is negative 36.667 kilonewton meter. Another way of computing that area, remember the tangent at this initial point is negative 15. So tangent of theta, this angle is negative 15 and it is opposite divided by 2. So therefore the opposite is negative 15 times 2. So that's why you have negative 30 here. Since the entire coordinate is negative 40, the distance from the tangent here to negative 40 is negative 10. So this area 1 is area of right triangle plus area of spandrel. The area of right triangle is 1/2 of 2 times negative 30, then plus area of spandrel 1/3 of 2 times negative 10. So the area 1 is also negative 36.661 by another way. You also compute the other area by another way, but I just use shear equation here to solve it because we ran out of space. But if you have time, do it by yourself so that you can discover many ways of computing areas or computing shear and moments in beams. Another way of checking that this area 1 is indeed negative 36.667, that's the moment just to the left of me. So you consider this load, the positive moment is counterclockwise, assume positive. So moment at B just to the left plus the moment of this rectangular load, which is 15 times 2 times 1. So that's plus 30, MB plus 30 plus moment of the triangular load 1/2 of 2. So that's already 1 times 10 kilonewton per meter. Remember, 25 minus 15. Then moment arm is 2/3. So 10 times 2/3 is 20 over 3 or 6.667. So MB plus 30 plus 20 over 3 equals 0. So you'll get MB just to the left, also negative 36.667 kilonewton meter. Just like the moment at D, if you isolate clockwise, the moment at D is positive clockwise. So moment at D plus 26 times 1 equals 0. So MD is negative 26. So that's why you have negative 26 here. So I hope that you know that. Without constructing the shear moment diagram, you can compute directly the negative moments which occur at the overhangs. So to continue, we have 0 initially moment to negative 36.667 area 1. So the initial tangent is horizontal because the ordinate here is 0. The tangent here is negative 40. Joining these points, this is negative 36.67 area 1 with a smooth curve, so that's the shape of the curve. Or you describe the change in ordinate in the shear diagram. It is 0 and it is increasing negatively. 0 slope and the slope is increasing negatively to negative 40 slope. So between this point and that point, the shear curve crosses that point where shear is 0. So let's define the shear equation for BC. So for section BC, this is B, that is C. So I'll call this W, and X is from here. So since this is 25, 45 minus 25 is 20. So our equation would be W minus 25, which is this, as to X equals 20 as to 4, because that's 4 meters. 20 over 4 is 5. So W is 5x plus 25 for that portion. So 5x plus 25. Therefore, the shear equation in this portion is 117, because this is 117, negative 40 plus 157. 117 minus the area of the trapezoid again, where the W is equal to 5x plus 25, and the W here is 25. So shear in BC is 117 minus area of trapezoid 1 half of x is from B. So 1 half of x times WB, which is 25, plus W here, which is 5x plus 25. Simplifying, share in BC is 117 minus 25x minus 2.5 x squared. Then we equate that to 0 because we want to find the value of x1 where the shear is 0, because it crosses shear is 0 before it becomes negative 23 from 117. So solving for x1 with your calculator, it is 3.4735 meters. Therefore, we can now compute area 2, which is the integral of the shear equation, which is 117 minus 15x, sorry, 117 minus 25x, then minus 2.5x squared, and you will get area to 220.661 kilonewton meter. Then area 3, same equation, 117 minus 25x minus 2.5x squared, but the limit should be from 3.4735 to 4, and you will get negative 5.994 for that area 3 there. That's negative, of course. Then area 4 is, because the tangent here is 0 intensity of load, so horizontal, so this portion of the curve is a spandrel of parabola where the area is 1/3 base times height. The height is negative 23 minus 67.5. That's why it's negative 90.5. So the height of this spandrel is 67.5. So area 4 is negative. It is area of rectangle. The area of rectangle is 3 meters by 90.5. Then area of spandrel 1/3 of 3 times, as I said, 67.5. And you will get negative 204. You just do it with your calculator. So make it negative. Make the area of rectangle positive, then minus area of spandrel positive also. The result is positive, but it is preceded with a negative sign because it should be negative. So again, area of rectangle 3 meters by 90.5, then area of spandrel 1/3 of 3 times 67.5, so you'll get 204 and make it negative 204. So finally, of course, this is 26 times 1. So from negative 36.667 plus area 2, which is 220.661, you'll have there 183.994 under the zero shear. Then to connect these 2 points with a smooth curve, initial tangent here is 117. Then the slope there is 0 horizontal. So of course, it should look like that to make it tangent to the initial slope to the tangent to the horizontal. Then 183.994 plus negative 5.994 is 178. So to connect then with a smooth curve, it begins with 0 horizontal slope to negative 23 slope. So it should look like that. Now, another way to check 178, it is, you just sum up moment here. It is 116.5 times 3, do it with your calculator, 116.5 times 3 minus 1 half of 3 times 45 times 1 minus 26 times 4, and you will get 178. If you are already expert in shear moment diagram, you can check that. So 178 plus area 4, which is negative 204, so you'll get negative 26. So connect these 2 points with a curve. The ordinate in the shear diagram is from negative 23 to negative 90.5, so that is negative increasing slope. So that's why you have negative slope, and it is increasing from negative 23 slope to negative 90.5. This is almost vertical, so that's why that's the smooth curve. So 178 plus negative 204 is negative 26, and finally negative 26 plus 26 is 0. Then join these points because that is 0 degree, this is first degree. Join these 2 points with a straight line. So that's it for this video. I hope that you were able to follow the explanations and the solutions.